Yes, so I'll ask Akshay sir to make you the host. Uh, yes, sir, you are now able to share the screen, so you are a
Okay. Yeah, okay, good. So should we wait for some more time, because it seems like people have not joined, right?
Yes, sir.
Okay, I'll try to join from another device as well, just for the checking. I cannot see.
Yes, sir. It is visible now, sir.
No, screen is visible. So, okay. So has people joined now?
Yes, sir. A couple of learners have joined.
The Google form which you had sent, can you mail that one to me?
Yes.
Well? Okay.
I'm doing it right away. Send, sir.
Okay. Fine. So, welcome everyone. So, how many people have joined right now?
So 3 people, and a couple of them are on YouTube Live.
Okay. So, so this is about discrete math, right? So we are looking at if there are any questions from you, we will try to answer it based on whatever you have seen, the videos which you have seen. Okay. So if there are any questions, please feel free to unmute yourself and speak up. Okay. So we can wait for others to join. For those who have already joined, if they have any doubts about anything, please let me know. We'll try to go over it if we can during this time. Yeah. So you can put your questions in the chat. If there are any questions in the chat, you please try to read it for me, Amit. Okay.
Yes, sir.
So are there any questions, guys? So this is your opportunity to see if there are any clarification you require based on the material covered. Yeah, I'm middle of something after 5. Yeah. Yeah, guys. Any questions? Any questions in the chat?
None yet, sir.
See, unless you guys ask anything, I have nothing to. This is not going to be like a class, right? So this is a live session. So it is for you to see based on the lectures, whatever you have seen. If there are any doubts or anything for you, we can go over it and then clarify them. That is the whole point, right? Okay. Anyone has any questions?
None yet, sir.
None yet. Okay, we'll wait for some time.
Yes.
Don't feel shy in trying to ask the question. Okay.
Yes, there's a question in YouTube chat.
Okay.
They are asking, can we discuss the puzzle that was given for the pigeonhole principle? Okay, there were a couple of puzzles. I'll ask the learner to be more precise. You know,
Yeah. What is the question? What is the puzzle?
yeah, I've asked the learner to
Mhm.
write and
State.
also the list.
Okay. So they haven't still given the question, is it?
Yes, the question is the 10-man problem. We're using pigeonhole principle. We have to prove that one of the sequence will be increasing or decreasing. So I think they are asking about the question where you have to prove that there are 10 numbers, and you have to put the less than and greater than equal to signs, either less than or greater than signs between them to satisfy that inequality. I suppose that is what they are trying to ask.
So are you? So let's see whether. Can they ask questions or means they can only ask questions through chat? Means they can speak up, or how is it?
Actually, the person who has asked the question is not in the Zoom meeting. He is on YouTube chat, so there he can only type and ask.
Okay. So I'm assuming you are talking about the following question. Maybe if I give a sequence of, I hope you guys can see what I'm writing. If I am given a sequence of, let us say, n square plus 1 numbers, then there exists a sequence of length n, which is strictly increasing or strictly decreasing. Is that the question? So
yes, I suppose that is the question.
So he said yes.
No, they haven't responded yet.
Okay.
So a couple of seconds lag in the stream and the meeting.
Okay. So
Yes,
okay.
this is the one they have confirmed.
Okay, good. So see, this question is a famous problem. I think it is called Erdo-Jacques problem. Okay, so what the question states is, suppose you have, let's say, 10 numbers. Here I'm choosing n is equal to 3. Okay, so let's randomly take 10 numbers which are distinct: 10, 12, 16, 9, 5, 4, 11, 1, 2, 3, 4, 5, 6, 7, 27, 1. How many are there? 3, 4, 5, 6, 9, and one more. So right now, let's say we put 4. So in these 10 numbers, okay, we are going to find 4 numbers which are going to be either increasing or decreasing. In this case, we can possibly say 10, 12, 16, 27. They form a strictly increasing sequence. If this is not there, then certainly the other one should be there. So in this case, luckily we have strictly increasing sequence. Does it have strictly decreasing sequence also? Let's see. Maybe we'll see 10, 12, 16. Okay, let's see whether we have a decreasing sequence. We have 9, 5, 4, 1, right? Yeah, so we have a length 4 strictly decreasing sequence. Okay. So, okay, so you want the solution to this problem or what? Okay, is that what they are asking?
They just said, I want to discuss about this puzzle.
What is the question? Do they have a attempt, or what do they want to do? Like,
I think they had problems to understanding the proof that it is always possible. That
how to do it using, so how to do it using pigeonhole principle, they are not fully clear. Is that what they are saying?
Yes, they said to discuss the proof. That's why.
Okay, so see, I'll give you a proof sketch. Maybe you can think about it. See, what you need to do is you can think of this 10, 12, 16 as some kind of length or radius or something, or area, something like that. So we will try to, as number comes, we are going to create piles. Okay, so I will tell you how to create piles. Suppose 10 comes, so you start putting that. So this assume that the area is 10 units. 12 means it's a bigger sized 12 units area, so I will put on top of it. When 16 comes, I'm going to put one more on top of it. Okay, now when something you try to keep putting it on the top of the number first. Suppose now 9 came. Okay, so 9 I cannot put on the top of 16. So what I do is I create a new pile. Okay, I start a new pile. Then again, now 5 comes. Can I put on top of the first pile? No, because 16 seems to be the largest value. Sorry. And then can we put on the top of the pile 9? No, that also cannot be done. Okay, so we cannot put 5 on top of it. So we need to create a new pile 5. Then next number 4 comes. Now we try again. 4 we try to put on top of 16. That will not work. Let's try to put on top of 9. We cannot do that. Can we put on top of 5? That cannot be done. 4. Now, as you can clearly see, you have got 4 piles, which is what we need really, which is the decreasing sequence. So how do we get that? So maybe we will try to complete this full process and then see what happens. Okay, so 4 comes, then we created a new pile. Okay, all right. So we got the desired thing, but we will proceed with the rest of the things and see where we are going. So 4 is there, then 11 comes. Can we put 11 on top of this 4? Yes. Can we put 27 on top of, yeah, we can put on top of this one. Yes, 1 when we come, we have to create one more new one. Let's say 4, one more 4, let's make it 41, the last number. So therefore, I can put on top of this. So as you can see, what I have shown is a construction of these numbers in terms of piles. Okay, so as you can see, there is going to be certainly a pile which will have height of n. Okay, there will be either a pile of height n, or you are going to have more than n piles. Why is this? Because there are totally n square plus 1 numbers here. Certainly we are going to end into the following eventuality. What is that? At least one of the piles, should have height n. Suppose none of the piles have height n, then what it means, this should happen, or there is going to be more than, that means strictly greater than n, more than n piles. Okay, so these are the 2 possibilities. In each of these possibilities, we are going to get whatever we want. Suppose one of the pile was having height n, so then you get an increasing sequence of numbers according to that subsequence you have got. So for example, in this case, 10, 12, 16, 27, 41, that gave you an answer. Okay, but suppose you don't get any pile of height n, so we certainly have certainly we are going to have more than n piles. Okay, so let's say n plus 1 pile. So why did this last pile appear? Because I could not put that guy on top of any other guy. So we are going to get a decreasing sequence by following this logic. So you can look at why the last pile has got created. I could not put someone on top of the previous pile. That is why this got created. So you go to that guy, whoever was there, and pick that fellow and see why this guy came here. That is because I could not put this guy on top of the previous pile because it was a smaller number. So if you reason out in this way, you are going to get a decreasing sequence. So this is a proof saying that either you are going to get n+1 decreasing number or n+1 increasing number. I hope this gives you an idea how you can prove this statement. Is that clear? So you can maybe see what the response is. Based on that, we can try to respond. Yeah. Are there other questions?
No, none in the chat.
Okay.
Learners have joined, but no questions yet.
Guys, see, it's your opportunity to please ask questions and then learn, basically, if you have any doubts over those materials. So did he follow the argument? Like, is he okay with this?
There is no message yet, but I suppose he would have understood. Yes.
Okay.
Yes, so the learner has said that, yes, sir, I got your point, but how are we going to decide what are the pigeons and what are the pigeonholes?
Okay, see, that depends on a given problem. In this problem, we have constructed in such a way that so you see, this is like a two-dimensional construction, right? So here, what do you think are the pigeons? So we have a matrix. Basically, we are having n²+1 numbers. Those are the pigeons here. So the pigeonholes are the matrix n cross n. Basically, you can think of this as each pile can have at max a height of n. So therefore, we are going to have, let us say, n² holes. So what we are saying is there are n²+1 numbers here. I'm trying to put it in this matrix. Certainly, there is going to be a column or a row. See, if a height becomes higher, that means we get an increasing sequence. If you have more number of, basically, if a length of a row becomes more than n, like this, then we are going to have a decreasing sequence. So that way, we are saying that the n²+1 numbers are the pigeons, and this matrix you can think of it as your pigeonholes. So certainly, there is going to be a row or a column which should have at least more than n length. That's all the main idea is. But how do we construct this matrix? That is what I explained it to you. So we keep putting one number on top of another whenever you can, but whenever you cannot, you create a new column. So we keep doing this, and that way you will be able to completely come up with an answer. So the difficult part in the proof, whatever I gave, is how do we get the decreasing sequence? So for that, suppose you have got n+1 piles. So what I'm trying to say is the reason why I created the n+1th pile is because there was all the numbers in the nth pile were bigger than this. So I have to create a new pile. So when I tried to put this number, there was one number which was bigger than this. You pick that number now in your hand. Take that number and repeatedly do this process. Maybe one example could help you. Maybe let's say we'll try to take a 5-dimensional example, means 7, 2. So let me take n is equal to 2. So then we have 7, 2. So I don't want to create any increasing sequence this time. 7, 2, 4, let's say 1. And then let's say 6. So let's try to do this. So first I'm trying to put 7. Now I cannot create a new thing on top of it. So I created one more thing. When 4 comes, 4 comes, even now I cannot put on top of 7. Now I go to the next one. I try to put on top of that. Then 1 comes, I create 1. So I put on top of this. Means I create a new pile because I cannot put on top of this. Now 6 comes, I cannot put on top of this. Neither 6 I can do here. Okay, so 6 creates a high 3. So let's not try 6 here. Maybe let's assume that number is, let's say, possibly, let's say 1.5 or 0.5 or 0. Let's take for simply 0 is a number. Then I cannot put a 0 on top of this, neither this, neither this. So already we have created a pile 1, but then we have one more thing, so 0. Okay, so to get the decreasing sequence, what I'm saying is 0 came here because 1 was here. So I will write it in the reverse order, 1. So now 1, why did it come here? When I tried to put 1, 4 was there, so I could not do it. So I take 4. Then why did the 4 come here? Because 7 was there. So I got a decreasing sequence, 7, 4, 1, 0. We have gotten it more than even length 2. Actually, we expect length 3. We got 4 now, but that's okay. Anyway, we got a length more than what we expected. No, that's fine, right? So I hope it clarifies. Is it okay? So please try to see if we are clear. If you have any questions, let me know. Okay.
Yes, I'll let you know once they reply. There's a question.
Yeah.
In so,
what is the?
Yes, so the question says, hi, good evening. The explanations were clear in the lecture video. I want to understand the solution for 10th question of week 1 assignment. There are 3 students from class A and 7 students from class B who are taking part in a hackathon in which teams of 2 participants each compete against each other. Find the number of ways we can form teams where each class A student is paired with a class B student and the remaining class B students are paired among themselves, which means a pair which has both students from class B. So this is an assignment question which they.
I don't think. See, we will discuss the answers to the questions. Will not be done. Okay. See, if you have any conceptual difficulty, maybe we can discuss that in solving some things. But we will not discuss the solution. That is not allowed. Okay. So if you have any confusion about how you have to solve a general question, we can certainly discuss. But let us not try to discuss questions from the assignment. Is that okay?
Yeah. So maybe they can, post it on the forum and I'll answer it in the evening.
Yeah. That you can do. Yeah. Maybe that also you cannot give the solution exactly.
Yes, once the assignment date has passed after that.
Yeah. Yes.
So the person from before has replied that, sir, does this logic work if the length of the sequence is not of the form n square plus 1?
Okay, so the generalization is, suppose you have, see, in general, what the problem states is you have a sequence of length m into n plus 1. Okay, so general statement is this: a1, a2, a3, and so on. Mn plus 1 numbers are given to you. So call this Mn plus 1 as capital N. Okay. Suppose you have these many numbers, then the problems ask you to, so they are all distinct. Assume all AIs are distinct. Okay. Then what the problem claims is, then there exists either an increasing sequence of length m plus 1. If that is not there, or there exists a decreasing sequence of length n plus 1. So basically what it says is, to give an example, let's take m is equal to 3, n is equal to 2. So m into n plus 1, capital N is 7. So if you take any 7 numbers, a1, a2, a3, a4, a5, a6, you pick any 7 numbers, whatever you want. Certainly there is going to be either an increasing sequence of length 4 or a decreasing sequence of length 3. If that is not there, this will be there. If this is not there, that will be there. Both can also be there. That we are not saying. Okay. But certainly one of them is there. That's what we are saying. So to illustrate it, you can, if you want to, I'm randomly, whatever comes to my mind, I am trying to write it down. Some numbers, maybe we will see what is going to come out. Okay. So let's say, see, let's take this random sequence. In this case, 10, 11, 13. It doesn't have an increasing sequence. So M is 3. So we want an increasing sequence of length 4. That is not there. 10, 11, 13. Is there any other way we can get 2, 4, 6? There is no increasing sequence of length 4. Therefore, certainly this sequence is going to have a decreasing sequence of length 3. So we will see that. So 11, 7, 4. So that is your decreasing sequence. 11, 7, 4 or 11, 7, 6. So we said that either we have an increasing sequence of length 4, which is not there in this sequence. You can see it. Okay. Therefore, certainly this 7 numbers will contain a decreasing sequence of length 3. That is clearly there. 11, 7, 4 or 11, 7, 6. There are other ways also, maybe 10, 7, 4, 10, 7, 6, many other things. Okay. Is that okay?
Yeah, I'll let you know once.
Yeah, okay. Are there any other questions?
No, sir, none yet.
Yeah, okay. So any questions, guys? So those who have joined in the Zoom, they have any particular thing you want to get it clarified? We can go over it. Any topic which you found it difficult, we can revise it. But unless you unmute yourself and speak up, we cannot do that. Okay. So please feel free to unmute yourself and speak up.
Yes, sir. They said that it is clear. Thank you.
Okay, great. Okay. Yeah. So any other question that has come so far?
No, sir.
Any other top? Yeah.
So yeah, I think the person, they are saying that this is week 1 assignment question. The solution is available. I understand the solution, but I feel there are many ways to think of the solution. What should be the right way to think of the combinations?
Okay. See, typically, whichever is convenient to you, you are supposed to use that method and then do it. But it is always a good idea to know how there are different ways to solve the same question, because sometimes whatever the natural way you're thinking may not work out for that particular question. So it is okay to certainly solve in whatever way is convenient to you. That is fine. But if there are multiple methods, it is better to learn all the methods. And when at a later point, when your own method will not work and those problems, you will be able to utilize the other method and then solve it. So it's good to know many techniques for solving the same problem. Yeah. I hope that answers your doubt. Any other question?
No, none yes yet.
Okay.
Yeah, somebody is asking, sir, can you explain how to solve problems dealing inequalities using mathematical induction? So this is the question that I suppose was the first one, but that was not what they were asking. So they are asking that suppose we have n numbers given and you have to put inequality sign between them. So this you can always put a sign that will satisfy the inequalities. You can always find such combination.
Can you pose that question into the chat here? It will be better. I'm unable to understand the question.
It's here in the chat, sir. The last question. Okay,
let me see. So this is not okay. So can you explain how to solve problem dealing inequalities using mathematical induction?
This is a completely new question, sir. Yes.
Okay, this is a different one. Okay.
Yes. Yes.
Okay. So see, in some cases, Okay, so maybe what is mathematical induction? It is a technique to show that something holds for all n. See, what is the kind of inequality question I am assuming you're asking? 2 power n, n factorial, which among them is bigger? Okay, sometimes you can solve certainly using induction. So is this true? For let's say n is equal to 1, it is 2 power 1, and the right side is 1. It is not true. But n is equal to 2, it is 4. And then the other side is, okay, so even here it is not working out. So which way? So I think this statement 2 power n is less than n factorial. So, okay, beyond a point, maybe will it, okay, wait, let's see. So maybe some factor we can have. Okay, so something like this you want to show. The other way, I will put the inequality, let's say this way. So you want to show that, let's say 2 power n greater than n factorial. I don't know. We'll have to see whether it is true or not. Okay. So for at least n is equal to 1, 2, it seems to be correct. N is equal to n is equal to 1, it is 2 greater than 1 factorial. 2, it is 4 greater than 4 greater than 2. N is equal to 3. So we have 8 greater than 6. Something like this we are getting, right? N is equal to 4. We have 16. 4 factorial. Okay. 4 factorial is 24, right? Okay. N is equal to 5. Is 32. This is not greater. So this is 32. Then 5 factorial is 120. Yeah. So this is greater actually. So let me read in the correct way. So what I wrote was fine. So we want to show something like this. Let's assume this is what we are observing. Okay. So what we are seeing at least is for n greater than or equal to 5 or 4, let us say here, we can clearly see that this is true. Right? 2 power n is greater than n factorial. That's what we are saying. Less than n factorial. Now you assume that this p of n is 2 power n less than n factorial is true. Then you need to prove that Pn plus 1 is true. So in general, what do you do now? What is Pn plus 1? We have to show that 2 power n plus 1 less than n plus 1 factorial. This is what you have to show. But what we have is 2 power n here, okay? And we have n factorial here. So what we, as long, so we have to multiply, let's say I'm going to multiply by n plus 1 both sides. So this inequality will be still preserved, right? So this I'm able to write from this. Since we know P of n is true, and then I'm multiplying by n plus 1, this is true. Now, if n plus 1 is greater than 2, then I can write this side as n plus 1 greater than 2. That for that we need n greater than 1. So then 2 power n plus 1 will be greater than n plus 1 factorial. So we have shown it. Is this clear? So we have, see, we need to make a statement. So in this case, 2 power n less than n factorial. That was the statement we were checking. Okay, so we checked a few cases. In first few things it failed, but we know that after some point it starts picking up. Basically, n factorial is much faster compared to 2 power n. Okay, so we want to prove it using induction. So we said P of n is that, and we assume that P of n is true. Then we want to show that 2 power n plus 1 is less than n plus 1 factorial. So for this, we took this and multiplied by n plus 1 both sides. And since it's a positive thing, we can do this. And as long n plus 1 is greater than 2, I can write the left-hand side can be written 2 power n plus 1 less than n plus 1 factorial. Okay. So we have shown using induction that these inequalities are true. I hope this clarifies. So you will have to see based on what kind of problem it is, and then see whether you can make a progress based on that. I hope that helps. Yeah. Any other question?
Yes, sir. There is a question in the YouTube chat.
Hmm.
Sir, in the videos, we talked about false proofs using mathematical induction. I
Hmm.
want to know how to identify such false proofs using induction. It was not
Hmm.
clear for me in the video.
Okay, fine. See, you have to understand. Okay, let's go over that example. But before we get there, Aditya Kumar Karna, did you at least understand what we did? Because you have asked this question. Since you are still here, I could directly talk to you. Okay, great. Okay, so the false proof using induction. That's what your question is, right?
Yes.
Okay. Okay. So what was that we were trying to prove? All. One second. So we want to show using induction all horses in the world are of the same color. Okay, so that is what we want to prove. Let's assume that we want to do that. Okay, so let me write the statement. Just give me a minute. Pen is getting stuck. All horse in the world is of same color. See, the problem you should understand is not with the method. It is about in the understanding of the method and employing it. So what is so this is what we want to show. So how we want to use it, induction, to prove it, we are going to say the following. Let P of n denote the any set of n horses is of the same color. Any set of n horses is of the same color. So this is my proposition. I am proposing that you take, let's say n equal to 10 horses, you take any 10 horses, it will be of the same color. This is not true, we know, but we are going to prove using induction. We'll see what is the problem. Where is the problem in the proof? Okay. So the proof goes like P of 1 is, there is only one horse. You take any one horse, any set of one horse, it is of the same color. So P of 1 is true. Okay. Now we will assume P of n is true and show P of Pn plus 1 is true. This is what we will do. Okay. So how are we going to do that? So since P of n is true, so P of n plus 1 is true. So you take any n plus 1 horses. That's what it is. H1, H2, H3, Hn plus 1. These many horses has been taken. Okay. This is my set. What I'm going to do is I'm going to take H1, H2 till Hn is one set S1. Okay. And S2 will have H2, H3. So by P of n, I know S1 has one color. All horses in S1 has one color. In S2 has one color, same color, one color. Now, but we know H2 is present in both S1 and S2. Therefore, S1 and S2 is of the same color. Therefore, all horses in S is of one color. S has only one color. So we have shown all horses in S is of one color. Okay, I hope the argument is clear to everybody. So what is the problem with this, whatever I have shown here? Anybody is able to see what the issue is? There is not, see, I verified the base step. I verified the induction step, which is Pn true implies Pn plus 1 is true. But then what is the problem here? There is a subtle point. That is what we want to show here. That is why this is a false proof by induction. Anyone? What is wrong here? Someone asked this question, no? Can you spot where the mistake is? Any response?
No, no, sir.
Mm-hmm. Maybe I'll give a minute so that due to delay possibly.
Yes.
Why all horses are not of the same color, we know. But what is the problem with the proof I have given, Aditya? Certainly we know we are not. We know that there is no question about it. but mathematically I have shown it, no? Either the induction is wrong or the proof is wrong somewhere. So certainly we know all horses are not the same color. How do we say that? Where is the problem here? Okay, maybe let me clarify that. See, in general, induction has two steps. One is called the base step, which says that at some level, basically base step is like usually P of 1 is true or some base case is true. And you have an inductive step. This is to be carefully understood. Inductive step says if P of n is true, implies P of n plus 1 true. This should be for all n. That is very important. If P of n is true, implies P of n plus 1 true. If I have shown for all n, then we are done. But in our case, what similarity is not same in two horses? Okay. See, okay, let me anyway clarify this. You see whether you fully understand it. So there are two steps. So here base step seems to be correct. P of 1 is true. Okay. But P of n is true implies P of n plus 1 true will work if n is greater than 2, greater than or equal to 2. If n is equal to 2, I will have two horses. If I assume there are two horses, H1, H2, okay, and if suppose P of 2 is true, suppose it is true, it implies that P of 3 is true. The way we have argued now. So if you pick three horses, if somebody gave H1 prime, H2 prime, H3 prime, I can certainly divide it into two baskets. Okay? And then another basket is H2 prime, H3 prime. In both these cases, P of 2 is true. Here also P of 2 is true. So therefore, it is of same color. Therefore, this also is of the same color. This is how the logic is. But the P of n implies P of n plus 1 is only true for n greater than or equal to 2. P of that is not true for n is equal to 1. If you suppose somebody is P of 1 does not imply P of 2. That is the problem here. So the false proof is coming because you simply assume for n and some n it is true, n plus 1 is true, holds for all n. It doesn't hold for the logic gets violated. The problem comes when n is equal to just 1. P of 1 does not imply P of 2. Let's take, suppose two horses are there. Okay. Let's call them, let's say H1 and H2. Now, if I try to pick set like whatever argument I have given, originally I had S. Now S1 will have only H1. This may be some other color. S2 will have H2. It will have some other color. Now S1 and S2 having different colors. So I cannot conclude S is having one color. That is not possible. Therefore, the problem lies in proving that P of n implies P of n plus 1 for all n is not done. Only for n greater than or equal to 2, it is true. But n is equal to 1, it is not true. Since if n is equal to 1 is not true, P of 1 will not imply P of 2. Therefore, P of 2 will not also imply P of 3. Right? So that logic will break there. If P of 1 imply P of 2 is not true, essentially P of 2 is false. Therefore, the further P of 2 imply P of 3, all these things will not work. That is where the problem lies. Is that clear to everybody? So the problem is in the induction step where we are assuming that logic works for any n, but it doesn't work for n is equal to 1. That is where the problem is. So you should be careful in dealing with induction and to be sure that this holds P of n imply P of n plus 1 works for whatever n we wanted to show. It is true irrespective of any n. It does not depend on a particular choice of n. It should be true. That is what we want to see from this example. I hope this clarifies for the person who asked this question.
Yes, I'll let you know once they respond. Meanwhile, there's another question. Sir, can we compare n factorial and n raised to the power of square root n?
No, you can compare. What is the question? I didn't understand. Can you paste it here?
Okay. Pasted.
Okay, okay. See, you can do whatever you want. N factorial, n power root n. Yeah. See, first of all, the question is n power square root n, which is bigger. Induction is a way to prove if you think that something is true or not. Means suppose you assume something is true, it is a way to do it. Sometimes it is easy to do it. Sometimes it will become very difficult to prove using induction. You will have to try it. In this case, you will have to see whether the same logic what we have done, which is bigger only, I don't know. We cannot say compare it. Induction is not going to give an answer. Induction is going to only give a proof if you know something is true. Suppose something is true, then how to prove it? Then you can use induction to do it. So that's all I'm saying. So in this case, I have no idea which is bigger, n factorial or n power root n, which is bigger, I don't know. For large values of n, which is bigger? Unless we plot this and see it for ourselves, we cannot clearly see it, right?
The person from before asked that, so you said that this false proof will break down for P of 1, but we have studied some examples where the base step itself starts from P of 2 or P of 3. Then how to distinguish between the two?
No. See, don't worry. 1, 2, 3 are just, see, you want to show, okay, can you just paste it here? It will be helpful. Okay. All the questions, if you paste it, it will be easier.
Yes,
See, first thing, induction is a technique. The technique is very simple. Don't worry about whether it is starting with P of 1 or P of 50. The problem was not P of 1 is true. That is not the problem. Please understand. The problem is with the implication. There are two steps. I repeat it. There are two steps. You don't think of that: base step and inductive step. Like that you think. Don't. So base step is, see, you want to prove some fact about P of n for some n greater than or equal to some n naught. Okay. Now the base step here will be, you have to show that for n naught it is true. We are saying that P of n naught is true. That is what is the base step. I want to show that n naught, let us say, is 100. I want to show that P of 100 is true. Once I show that, and I show the following, that is P of n implies P of n plus 1 for all n greater than or equal to 100. If I show this, then we are showing that P of n is true for all n greater than or equal to 100. That's all we are saying. So how is it logic? P of 100 is true, we know, and we have shown that P of 100 true implies P of 101. We have shown that because that is what is the inductive step doing. Then we know that by our induction, again, P of 101 will imply P of 102. P of 102 will imply P of 103, and so on and so forth, and everything will be true. So it is like a domino, they say, no? Domino effect. So the domino starting point could be 1, 200, anything it could be. Something has, if one domino falls on another domino, that is the induction step, inductive step. If that happens, that domino will fall on the other one. That is what you have shown in the induction, right? So if one domino will fall on the next piece, then that domino will fall on that one. That will eventually happen. So everything will totally fall. That is what the whole idea is about, right? So don't get confused yourself with what is base step or anything. So you want to prove some fact about, for each n, something is true. That n will take some range. N may take range from 10 to infinity or 20 to infinity, doesn't matter. Okay. So what we are doing is, first we prove that 10 it is true. Yes. Okay. And then we show that if 10 is true, 11 is true. That is what we are showing in the inductive step. And the inductive step is not only showing that, it is showing that 11 implies 12 also. So because 10 implies 11, we have shown by the induction, 11 implies 12 also automatically holds. Therefore, 12 implies 13 also holds. So therefore, everything holds. That is what you have to understand. Hope it clarifies. Is it okay?
Yeah, I'll let you know once.
Yeah. Are there any other questions? Yeah.
No, sir. No other questions yet.
Okay, so we'll wait for any further questions. See, you guys have another 10 minutes. It will be a good idea to see if you can utilize this time, if you have any doubts. Okay. Yeah, if there are no questions, we can end the session earlier, but I'll wait for a few more minutes and see if there are.
Yes, and says that got it. Thank you.
Okay, great. Okay, good. Those who have already in the Zoom call can please unmute and speak, because you have a good opportunity to directly interact with me. And if you have any doubts on whatever you have studied or any other related stuff, you can tell me. Okay, what is this? Some P or Q or see, you will have to remember, right? See, what the question is, conjunction and disjunction, right? See, typically you need to understand there are two things. So this is equivalent to P into Q, P and Q. And this will be P plus Q. So this is conjunction. This is disjunction, right? So unable to identify why the symbol bar below disjunction symbol. Why? What is that? I don't know what you're talking, Anil Kumar. Where is it like that? Okay, I thought something else. So this is was going to tell you.
Suppose they mean the XOR symbol, but I'm not sure.
No, you cannot put under this one. There is nothing. You cannot show anything. Nothing. Yeah. It is on the variables only. You can do negation. I'm not sure.
There's a new question in the chat too. I'll say in the chat, Zoom chat.
In this Zoom chat, yeah, I see it. Can mathematical statement which is false be proved true? Because in the example we were shown a statement which isn't mathematical. What is it? Can you tell me? Can you please explain yourself? I don't understand your question. You can unmute yourself and speak up. Yeah. Aditya Kumar Karna.
Like there is a mathematical statement like something is equal to something, which is actually false. Can it be proved true using mathematical induction?
No, you cannot. It is a false statement. How can you prove through any method? Mathematical statement only proves correct things. That's what I have told you. It is not even a method to see which is bigger or smaller. Okay. There is no way you can prove a wrong thing using any technique. That means the proof is wrong. Somewhere in the proof, there is a mistake. So if a fact is false, see, if fact is true, you can give a false proof for it. That is possible, but that is also not allowed, right? That is also not allowed. And if fact is certainly wrong, then if you have given a correct, perfect proof, that is not possible. It is wrong. The proof is wrong somewhere. So you will have to find out where it is wrong, or the technique which you have used is wrong somewhere. So one or the other thing should be happening. Okay, so we cannot prove the false things using, just because we have math, we cannot prove false things. That is not possible. It is impossible actually. Okay, so I see one more question. Is there any trick to identify a bipartite graph? So you know this coloring, no? If I can color a graph with two colors, then we can do we can make it as a bipartite graph. So you can try to see if you can color the graph with just two colors. That is one way to identify a bipartite graph. Hope that helps. So is it okay? So you given a graph, see if you can color the graph with just two colors. You start with something and see whenever it's a neighbor, you try to give a different color. If you can do this, using just two colors, then it is a bipartite graph. If you cannot do that and you require more than two, then it is not a bipartite. Is it clear? NOC23, there is someone has asked.
Yeah, I posted this question. This was from the YouTube chat. I'll let you know once they respond.
Okay, okay. So any question, guys? Any other questions?
No, sir, no questions now, as of now.
Okay. So, all right. We have few more minutes. Let's see if there are any questions.
Somebody asks, what is proof?
Is it in this chat or the other one?
YouTube chat. Just what is proof? That's all.
Okay. See, a lot of philosophical things. See, there is a statement we have made. Okay. See, what is a proof? Typically in math, there are some set of axioms which we assume to be true. And based on that, we are making some conclusion. If these axioms are true and we employ that, and we try to come up with a final statement, that we are going to call it as a proof. Directly on looking at it, it may not be obvious. So for example, okay, 1 second. So you have this Pythagoras theorem, right? We know that in a right angle triangle, c square is equal to a square plus b square. Somebody says, you take any right angle triangle, you take its hypotenuse and square it, you add these two squares. Obviously, whatever measurement you are doing, it will be true. But how do we know that this fact is true for all times? So for that, we are going to make some basic assumption about not directly making that statement itself as my axiom. So there are some basic axioms which will say that sum of angles in a triangle is 180 degree. Such basic things we are going to start with. Okay. And using that, we are going to conclude that c square is equal to b square plus a square. So you must have seen a geometrical proof for Pythagoras theorem, right? You try to embed 4 right triangles in a rectangle and then you can show it. So that is a proof for Pythagoras theorem. So basically from basic facts, we are concluding some other fact. That is what? It's like an inference we are doing. Okay. I hope that is helpful to understand what exactly is a proof, right? It is like making an inference based on the known things, something which is not very obvious. So then we have concluded some fact and we have also given a proof for that. I hope that is, I hope you understand.
There are a couple of more questions. Sir, can we discuss about algorithm to determine a Eulerian trail? I'm talking about Fleur's algorithm.
Can you just paste the question here?
Yes, sir.
See, there is, what is the algorithm here? See, we know already, okay. So it's not anyway part of our thing, right? Isn't it? So why do we need, see, we can find out given a graph, whether it has Eulerian circuit or not using the condition, no? So what is that you are trying to do? Can you please clarify that?
Yeah.
I don't.
Meanwhile, there was another question, so I pasted that.
Okay, let's see the question. What is the question? So we can, so see, I don't know the Floyd's algorithm. Okay, so I don't know what you're talking about. See, basically we have a condition to check for Eulerian circuit. So if the degree is even, then it has an Eulerian circuit, right? Every degree of all the vertices are even, then it is okay. If degree of at least, if except for one odd vertex, one vertex which may have odd degree, one or two vertex, I think you can have odd degree, two vertices having odd degree, then you are going to have an Eulerian trial. So that conditions are already clearly given to you. So you can check based on that. I don't understand what algorithm you are talking about. I have not heard about this algorithm, what you're saying, but yeah. So am I right saying K5 and C5 do not have any cut vertices? Okay, so I think you can answer this
Yes, sir.
maybe later, maybe not now. Okay, cut vertices or not, you can check it.
Yes, sir.
Okay, so you can discuss that in the chat. Guys, I think we are running out of time. If there are any final questions, I would like to answer it. And if not, you can certainly get back to the TAs and they will try to help you out. Okay. Yeah, so if there are any final questions, let me see if you have anything, and otherwise we will, because it's already 5 right now. Okay, so we will end the session now. Sorry.
One question, I want to find how a graph is Eulerian, but you have already answered that.
Okay, great, fine. So yeah, you can look at the corresponding section in the course, then you will possibly be able to understand, or you can look at the Kenneth Rosen book for more details. Even proofs are also given there. Why it is an Eulerian graph requires even degree vertices only. Okay. Okay. Anything else?
No, sir. There are no more questions in any chat.
Okay, guys. Thank you so much. Okay. So if there are any further questions, please get back to the TAs. They will try to answer. Okay. All right then. Okay. So we'll end the session, right, Amit?
Yes, sir.
Okay.
Yes.
So I will. Yeah. Okay. Thank you so much. Yeah. Bye.
So we can end the section. Akshay sir, we can end the session and live stream now.